Do you know what these seemingly simple lines of code are doing behind the scenes? Let's take a closer look at one of them. Given this program, what do you think happens behind the scenes? Think for a moment. We have our program on the disk, which we compile using a C compiler. The compiler goes through multiple phases: analysis, code generation, linking, and then it stores the compiled program on the disk. Next, loader moves it into the RAM for execution. The operating system schedules the program and starts running it. Based on the instructions, the CPU prints the text. When the program exits, the OS performs a cleanup. Pretty much what happens. Thanks for your time. Wait. What did the putS function actually do? How does it even know how to output text on the screen? Let's try to reverse engineer our application to find out. We can pass the -s parameter to the GCC compiler. Here's the cleaned up version of the assembly code. Don't worry, we'll go through it together. We can see a label with a string constant, followed by the setup of our main function. Here we store the base pointer and copy the stack pointer onto the base pointer. This is the function called setup. We'll come back to this later. Next, we see the address of the string being copied to the EDI register and a call is made to putS. Then 0 is copied onto EAX register to indicate the return code and the base pointer is popped since the function is complete and we finally return. That's it. Where's the definition for putS? It must be linked, but how do we know which library provides putS? To find, we can analyze the binary using ObjectDump. ObjectDump is a binary analysis tool that can help us disassemble binaries, inspect symbol tables, examine headers, metadata, check link libraries, and much more. Let's run ObjectDump. We can see the binary metadata and headers. We can also see dynamic section linking to libc. Interestingly, this might be the source of putS function, but we need more evidence to confirm it. Navigating to the symbol table, where compiler stores the address of identifiers, we also have a putS entry in the symbol table. If we scroll further, we can see dynamic symbol table, which includes the symbol from link libc, such as libc start main and the actual location for putS, which confirms our putS is coming from libc. Another interesting thing to note is the presence of start function, which references our main function. All of these details are normally abstracted away, but under the hood, the linker always sets the program entry to start, and libc handles the rest. Great! Now that we know putS is actually coming from libc, let's look at one of its implementations to dive deeper. What we are looking at is muselibc, which is one of the libc implementation. We can see putS, which locks standard output to prevent multi-threaded applications from stepping on each other's output. So once we have the lock, we can see a call to fputS, writing a string to standard output, followed by a putchar call to output a new line character, and then unlocking of standard output. Following putS lead us to fwrite. Fwrite locks the file, invokes fwritex, and then unlocks the file. Fwritex then writes the string using files write function. To dive deeper, we need to understand what this function refers to. Let's open fdopen, which helps us open a file to see the linked write function. Here we see that the write function is linked to stdio_write. Then we see the data passed to the syscall function. While exploring the definition of syscall, we encountered nested macros, until finally we see that the syscall compiles down to the assembly code using the syscall instruction. Let's fire up a debugger and dig deep into how it all works at the CPU level. The tool we'll be using is GDB, which stands for GNU Debugger. It's a powerful command line debugging tool used for programs which compile to machine code. This is the GDB terminal user interface. The top section consists of the CPU registers, middle section is the assembly code, and the bottom section is the GDB command line. We have a bunch of registers here. Let's quickly skim through some of the interesting ones. You remember RBP and RSP? These are the base pointer and the stack pointer registers. Base pointer stores a fixed reference for the current stack frame, while the stack pointers points to the top of the stack and moves as the values are pushed or popped. We will see how these values change as we progress through. Just note that currently the base pointer and the stack pointer are the same. Another set of interesting registers are RIP, which is the instruction pointer, similar to the program counter, which stores the address of next instruction to be executed. And we also have eFlags register, which indicate the carry, overflow, or similar signals. Let's continue the execution of our program. After executing a bunch of instructions, we finally reach the actual putS code. Skipping to the interesting code, we see IO wrappers for putS, which also does a bunch of malloc calls for allocating buffers and iterates over the pass string. Finally, we reach the libc write and we see the syscall. Here, RDI is the first argument, which contains 1, which denotes the standard output. The second argument is the RSI register, which stores the address of our string. We can do x/s to inspect the memory, which shows our string. The third register is RDX, which is the length of the string. Values of these registers match to our ideas gathered from the source code. These are documented in the Linux kernel source code. Now that we have verified our findings, we can see that putS calls are actually defined in libc, which in turn uses the kernel system call. These calls are captured by the kernel and matched against the syscall table to dispatch corresponding instructions which are propagated to the device drivers. So, the kernel acts as a resource manager and the application requests kernel to accomplish their tasks. When the application is running in the user mode and makes a syscall, the CPU saves the state and switches to the kernel mode. Exploring the kernel and see how kernel captures the signals and delegates it to the device driver can be its own deep dive. Wow, that was some real work done behind the scenes. If you're curious, Linux kernel source code and eBPF are your friends. Thank you so much for your time. I hope you learned something new from this video.